All right, so this is going to go through not the entirety of the review guide. It is a pretty lengthy one, but it's going to just make sure that we hit all of the kind of the nuts and bolts of Unit 3 in our chemical bonding, especially as it pertains to differentiating between ionic and covalent bonding, naming formulas, and so on and so forth. So the first couple are just kind of setting us up for a little review on valence electrons, some review from Unit 1 with protons, neutrons, electrons, and going through how those are all interrelated. So what are valence electrons? Of course, valence electrons are the outermost electrons, right? Outermost electrons based on the electrons that an atom has and which ones are on the furthest shell. And how can we find how many valence electrons? They're found based off of group number. So found based on group number. And so the groups that we're specifically talking about are the groups from, if you remember electron configuration, the S and P blocks. All right, and we can only have up to 8 electrons out there. And those first two are, of course, the S's are the first two groups, alkali metals, alkaline earth metals. And then the other main group elements are those P's, which are, and the way that we kind of go through is using 13 through 18 because we label each group as its own individual group on the periodic table. And so that'd be 13 through 18, or if you're looking at a different periodic table, it'd be the main groups 3A through 8A. So what is the octet rule? Kind of looking at our prefixes here, oct 8, 8 electrons in the outer shell, right? So 8 valence electrons. And that's what everything aspires to have, just like the noble gases. Of course, the exceptions are hydrogen, which only wants 2, helium, which doesn't react, but still is in that first row, that first period, so wants 2. And actually, we did say boron, which does use 6 in terms of the lack of electrons that it has to begin with those 3. But those are pretty much the main exceptions. This is the one that we need to really focus on right there is hydrogen. I like using just comparing metals to nonmetals this way as well. We know, first off, that protons never change because that would change the identity of the element. So when I'm talking about metals versus nonmetals here, metals on the left side of the periodic table lose electrons and form positive ions that we call cations. Nonmetals, of course, then gain electrons and form negative ions that we refer to as anions. And the reason why lose means positive and gain means negative here is because electrons, of course, have a negative charge overall. So if we lose those electrons, remember the protons, which are positive, stay the same. Stay the same, right? And that's in any element that we're looking at. So if you take magnesium, for instance, magnesium, and I'll kind of hone in over here, magnesium, which has 2 valence electrons normally, has 12 protons because its atomic number is 12 and 12 electrons. Now, these 2 electrons, it wants to lose them because then it'll feel full due to its inner shell. And it'll transfer them, of course, to a nonmetal that wants to gain. And when that happens, magnesium still ends up with 12 protons, but then ends up with 10 electrons total, and we see that because we have 12 positives still, we are more positive, and by 2 because we have 2 additional. So that's the idea behind why lose means positive, gain means negative there. And of course, define cation and anion. Cations are the positive ions, anions are the negative ions. Positive ions are all metals, so you can have our magnesium, you can have sodium, you can have our transition metals where iron can be a positive 2, iron can also be a positive 3. We do have a positive polyatomic that acts like a metal, so to speak, which is ammonium, all right, NH4. And then, of course, our negatives are going to be nonmetals, so something like oxygen that forms a negative 2 charge, phosphorus, negative 3, chlorine, negative 1, all the other halogens as well, and then our polyatomics that make up most of our groups, which are negatives, so nitrate, sulfate, phosphate, so on and so forth. Throwback, what happens? We've already touched this. If we change the number of protons, then we're changing the identity. So change in number of protons changes the identity of the element, right? And we can't do that when we're focused in on an element that we're already working with. And then, if, of course, number of neutrons, this is all for protons, changing the number of neutrons, remember, neutrons only contribute mass in the nucleus with the protons. So if we change the number of neutrons, change in number of neutrons changes mass number, which is why we get what we called isotopes, all right? The different variations of atoms in their masses based on what occurs naturally in the world. In this diagram, we've worked on how these ionic bonds form. And remember, ionic bonds aren't actual physical bonds that connect a cation to an anion. They're actually just put together by this positive side that really gets attracted to this negative side, right? That's what holds them together at a strong electrostatic force of attraction. So that's what occurs to create what we call an ionic bond. But how are those formed? Well, it's because, like we set up here, the metals that lose those electrons, they don't just go away, and the nonmetals gaining electrons don't just get them from nowhere, right? They actually you can say work together to create these ions. So calcium has 2 electrons that it wants to lose, and it finds a chlorine that wants to gain them, and they work together, of course. But you know that chlorine only wants 1 more, right? And then this electron then has nowhere to go, so we'll just need another chlorine there that can take that electron, that second electron that calcium has. And that's how we end up knowing that we will create 2 -1 ion charge chlorines that can balance out that. Because, of course, the positive and the negative overall, positive and negative, have to equal 0. Right? Because they have to balance each other out. 2 -1s make a -2. 2 plus -2, of course, is 0. So that's how you can check that. So that's kind of an explanation there. The key has it a little bit more written out, but that's the crux of that. And so let's do an example of that so you can actually see it in action. So here we have a magnesium and a bromine atom, and I want just the Lewis dot diagrams, which is just valence electrons only. And so magnesium has 2 valence electrons, and bromine, of course, has 7. And I say show using arrows because there's an electron transfer going on, a transfer between the metal, magnesium, the nonmetal, bromine. One loses, one gains. And what it looks like is similar to above, where we have something that wants to gain 1 electron while we have something that also wants to lose 2. Well, magnesium transfers 1 to that bromine. That bromine is now full. And so what we need to do is find another spot for that extra or that additional electron to go. And that means that we need something else that's going to take that electron, which, of course, is just going to be another bromine. Right? We can't just add another element out of nowhere. We have to work with the elements that are trying to bond together. And when this occurs, that's when we get our ionic bond, because that is when the ions are formed. And so the magnesium that lost 2 electrons is now more positive by 2. And we have the bromine that has now a full octet because of that additional electron that has a -1 charge, and this one does as well. You might see this with brackets around those as well, just to keep it a little bit cleaner. You can add the brackets if you would like, but again, the same rules apply. +2, -2, that's going to add up to 0 for the overall charge, which is the end goal there. And with a nice image there, we can identify what the formula should be, which is 1 magnesium ion for every 2 bromine ions. So that's our compound formula there. Of course, we did some simplification of that when we talked about taking our ion charges and the actual values and kind of just doing a little crisscross there, because that does balance out the charges as well. So you could do it that way as well. But now the name for ionics, and we know that magnesium here is not a transition metal, so it can only ever be a +2 charge, since it'll always have those 2 valence electrons. So we never change the name of the first element in ionic cases. The vast majority of the time it's going to be a metal. And bromine, we do have to change the ending of bromine to show that it has officially bonded with that magnesium. So we change it from bromine to bromide. And if you have a nonmetal that's bonding, and this should say bromine, I apologize, typo. But because you have this bond occur, we have to show that it was successful in doing so. And you have a nonmetal by itself, like bromine, chlorine, oxygen, any of those that are nonmetals that are not a part of a group, a polyatomic group, we just change their ending to "ide" there. And now in this case, now we have nitrogen and hydrogen. Now we know that both of those are nonmetals. So what this tells me is that up here, this is all forming an ionic bond, right? It's ionic bond because magnesium's a metal, and there's this transfer that occurs. Now, when we have these nonmetals, remember, these are going to be how our covalent bonds form. And so this is going to be a covalent bond, which, again, doesn't transfer. Nitrogen doesn't want to lose its electrons. Hydrogen prefer not to lose its electrons. And so what they end up doing is working together and sharing with one another. So what I need to do to figure out the formula is figure out how many hydrogen would be able to satisfy nitrogen's octet by sharing their electrons with each other. And so I start off with just saying, okay, well, hydrogen has 1 valence electron to share. Nitrogen has 5 valence electrons. You can see 2 of which are paired, right? We call that a lone pair, whereas there are 3 electrons that are not paired with anything yet. And so what this tells us is that nitrogen can actually create up to 3 covalent bonds because they have the availability based on those unpaired electrons. And so what I can do is I can say, well, since every hydrogen can only share 1 electron, well, think of how many hydrogen I am going to need to be able to satisfy nitrogen's octet, right? And what we end up seeing is that this hydrogen would be able to satisfy there, right? But then we'll need another one here, and then we'll need another one here, right? So that would be a total of, that would be a total of 3. So that's how we know that when nitrogen and hydrogen bond, more often than not, if we're talking about not a polyatomic ion here, right, just covalent bonding, we would, hello, we would have NH3, right? And so then we go and say, okay, well, the compound name, and for covalent bonding, remember we have our prefixes. Well, there's no number there, which of course means 1. We don't write ones, but that also means that we don't use the prefix mono on the first element, right? That was one of our rules. So we can just take nitrogen's name and just name it as is. And then, of course, because of the 3 here, we are going to end up with the prefix tri that represents 3 from our Greek prefixes, and hydrogen, well, we can't name it hydrogen. We have to change its name, and that's why we end up with hydride. So we have nitrogen trihydride here. And so let's see exactly what happens when this ends up creating an actual bond with these covalent shares of electrons. So we have nitrogen. Nitrogen, we have said that it has 5 valence electrons, can take 3, right, of its unpaired electrons to share, and hydrogen only has 1. So what we're going to do is we're going to come over here, and we know that nitrogen has to be the central atom because it can form the most covalent bonds. So we're going to put that one right in the middle. And so the sharing, right, the sharing, not transfer, is going to happen between hydrogen and nitrogen, and of course we identified that we would need 3 hydrogen in order to do this. And so what we did was we just showed a nice little circle, right, showing those unpaired electrons then that are going to end up pairing up and creating our covalent bond, right? And so I'm going to do that a little bit differently here. And actually, because we did it one way in class, I'll do one way this way, and then I'll actually show you what it looks like when they are shared aside from these. So, of course, we have our areas that we're going to share electrons with one another, right? So we have those. Those are the bonds that are going to form. But what that looks like is this hydrogen actually goes and says, yeah, I'll share this with you, nitrogen, as long as you share that other one with me. And nitrogen happily obliges. This hydrogen does the same. And, of course, this hydrogen does the same there. And so what we see is that nitrogen itself has a full octet now. And, of course, hydrogen, that's an exception to the octet rule, has the 2 electrons that it wants to make it feel like it is full. So what we have to do is make sure that we note that this is great to show, but we do want to replace those shared regions with actual bonds. So this region, where there is an active sharing going on, our final variation of this would show those regions as actual bonds right here, where each of those regions with a bond represents an area where 2 electrons are shared, right? Every bond represents 2 electrons being shared between those things. All right. So moving on. Again, we've talked overall charge needs to equal 0, right? The positive and the negative ends need to be even, so to speak, even but opposite. Our polyatomic ions here, remember, little English lesson, right? Poly means many. The root atomic mean atom. So we like to call these many atom ions, atoms that are grouped together to give us an ion charge, right? We find those for us in the back of our periodic tables. So many atom charge or many atom ion that have charges, right? So an example can be any of the ones that we've used. Nitrate, right? This is nitrate. We can have sulfite, which is SO3, -2 charge. We can have, let's say, hydroxide, right, which does end in IDE. However, hydroxide and cyanide, there are some polyatomics that do have that "ide" ending, but most of the time, we're really going to focus on the ones that end in "ate" and "ite," right? ATE, ITE, and that's how we know that we don't have a nonmetal by itself that we're changing the name of, right? Like sulfite is different from sulfate, which is another polyatomic group. And then you have sulfide, which is sulfur, it's just changed endings, so that's sulfur by itself. Sometimes they'll have the same ion charge, and sometimes they might not, kind of like nitrate has a -1 charge. Nitride, which is just nitrogen, has a -3 charge, right? But not to confuse, I'll get rid of that last one. The difference between naming alkaline metals, alkaline earth metals, and then transition metals is the transition metals require Roman numerals, right? And why? Why do they require Roman numerals? Well, because they can vary in charge, right? Vary in charge. So what does that mean? That means that I have elements that are in the very middle of our periodic table, and even under the little staircase that the metalloids are in, which they don't always have the same number of electrons that they're going to be losing, depending upon which it is. So copper can be +1 or +2, or lead can be +2 or +4, right? And so when we name these, the reason why it's so important to identify what their charge is because they need to be, you need to identify in the name which version, so to speak, lead or copper or any other transition metal took of itself, based on what it wants to bond with, and so on and so forth. Which elements are diatomic? Remember, diatomic, that prefix di means two, which means that when they're by themselves, they need to exist as a pair. I like to say honkel, briff, right? These are the 7, and whenever we see them that are by themselves and not paired up with either themselves or something else, they have to exist as a pair. So when we would write them, we would say this is actually not H, it would be H2, right? Or O2, so on and so forth. So those are the 7 there. Properties of ionic compounds. Again, properties or characteristics for these are how they act and what they do. Because ionic compounds have a metal, we can say that they are conductive in solution. And remember, we said that in solution means when it's dissolved, kind of like we did in our lab with sodium chloride, where the sodium actually ends up kind of breaking apart from the chlorine ions that are there, chloride ions, and that metal piece is what allows it to be conductive, because metals are conductive, which would mean that, of course, covalents are not conductive because they're only made up of nonmetals. So they're not conductive in solution. I would say that based on our lab as well, high melting points. You could also say boiling points as well. It takes a lot of heat because ionic compounds are so strong. Whoop. A little too fast. Strong, whereas covalent compounds are weak, right? Or weaker. So high melting points, which means these had low melting points. Our sugar definitely melted a lot quicker than our salt, our sodium chloride. And then last one, I think, is the biggest one that I'm going to make sure that we highlight, is formed by transfer of electrons, right? From metal to nonmetal, right? That's why we get the positive and the negative ions that form, right? Their ionics are formed by creating ions, right? And then we have, of course, these are formed by sharing electrons, right? These nonmetals that exist, they don't have the want to get rid of their electrons. They're the ones that want electrons, so they don't transfer, they share. and that's why they can come together and pair up any unpaired electrons that are. So, of course, the metal and the nonmetal, and then, of course, we have nonmetal plus nonmetal down by the covalence. Single covalent, single, double, triple. Remember, each bond, if we were to look back up here, each of these bonds that form through covalent bonding represent areas where 2 electrons are being shared. So if I had a double bond, like what carbon dioxide would have, then there would be an area where elements are bonded with 4 electrons, 2 pairs there. And then, of course, a triple bond would be 6. All right. And this is going to be the kind of, like I talked about nuts and bolts before, but this is where we kind of put everything all together based on, now that we're a little bit more comfortable with how to identify how those ionic compounds act, how those covalent compounds act, the difference in their bonding here, and how these bonds are formed, what we can do is come down here and we can start identifying, because, of course, different types of bonding require different ways to write formulas, different ways to write names. And so as I go through, I'm going to use what I know, whether it's ionic or covalent, to then get the correct formula or name. We do have a lot of rules, and so it would be good and beneficial for you to make sure you go back into any notes that we had to be able to kind of look off of as you're going through this. But the first one's oxygen gas. Now, I know oxygen's a nonmetal, and oxygen is the only thing we have there. Oxygen nonmetal, so I know it's covalent, but then I say, okay, well, oxygen gas, well, what does that mean? Well, remember, oxygen is by itself, but oxygen is one of the 7 diatomics that we have, so when they exist by themselves, they need to make sure that they have a partner, so we have O2. All right. Now we go over here, we see that we're given sodium. Now I see sodium is a metal, and I know that because of its location on the periodic table. And so I know that I have an ionic compound here. Now because I have an ionic compound, this is where I'm going to have to, in order to write the correct formula, I'm going to have to balance ion charges, right? Ionics allow us to create these compounds by making sure that that overall charge is 0. So I have to identify what these ions are. What I see is, because this is a chromate, right? Chromate is going to be a polyatomic group that I find on the back of the periodic table. Sodium forms a positive 1 charge. Chromate forms a negative 2 charge. Right? So when I put these two together, I have to make sure that the positive balances out that negative. The easy way is to do our little crisscross method. Or, of course, if we really wanted to, and I'll show you this little trick. Remember, we want sodium. Sodium is going to be represented by just 1 line, because it has a charge that's equivalent of 1, whether it's positive or negative. We use 1 line for that. And the chromate ion is actually going to represent 2 lines because it has a charge of 2. In this case, it is negative. So we need to fill the puzzle. We know that we need another sodium ion, and now we have our nice little full square. Sometimes it ends up becoming a rectangle. But then we're going to go back and we're going to say, hey, look, I needed 2 sodium to balance out the charge of 1 chromate. And that's how I'm going to write the formula. Na2, because I needed 2, and CrO4 for chromate. And even though we only need 1, remember, the polyatomic groups are as they come as they are, right? And so this 4 is a part of chromate. That's what makes it chromate. So we can't just say, oh, I only need 1, get rid of that. That's not how that works. This has to stick together, right? And we'll see what happens when we need more than 1 of them a little bit later on. Carbon dioxide, carbon's a nonmetal. Dioxide or oxygen's a nonmetal. So this is covalent. Another way we can do it through the name is knowing that, hey, we have a prefix there. A very important thing to note is that when we're writing the names, ionic do not use the prefixes, right? Whereas covalent do use the prefixes. All right, and so we know this is covalent. Di means 2, and since there's no prefix in front of the carbon, that's just going to be 1. So we have carbon and 2 oxygen together. Potassium's a metal. Ionic bromide, this is going to be a bromine ion. I know it's bromine and not bromate or bromite as a group because the ending IDE tells me that. So it's bromine by itself. And look at that. 1 and 1. Love it. All right, just putting them together. Dioxygen monochloride, again, prefixes and the fact that they're both nonmetals. 2, 1, 2 oxygen, and 1 chlorine. Iron 3, remember, our transition metals, like iron, they have to pick a charge, and this is a metal, so this is ionic. And we say, all right, this is iron with a positive 3 charge. Sulfate is not sulfur by itself. The 8 tells me that it is a polyatomic, and it's actually SO4 with a negative 2 charge. And we do our crisscross method to make things a little bit easier for ourselves. And we have Fe2 and SO4, but because I need more than one, right, we need 3 of them, I need to put it in parentheses to show that that identity does not change, and I need 3 of them. So whenever we need more than one polyatomic, we have to have those parentheses around it. And you can kind of see that happen over here. Right? What is this? Well, now I'm going from formula to name, but I still, same rules apply, look at the first element. And it's a metal, strontium, and so that is ionic. Another way you can think of it as only ionics that we name and write formulas for can have 3 elements, because if it has 3 or more elements, that means that we have a polyatomic ion. That word ion tells me, hey, this is going to be ionic, right? Because that's how ionic bonds are formed, through ions. And so we have strontium. Strontium is not a transition metal, so we do not need Roman numerals like we did for iron in the example above, because it always takes the same charge. And we identify what the name of the polyatomic is, which is hydroxide. You're going to be compelled to take hydroxide, see that there's 2, and put dihydroxide in front of it. But again, that would be incorrect because this is ionic. We do not use prefixes for ionic compounds. So we just name the secondary element or polyatomic as is. Over here, we see that we have 4 elements here, which means we have 2 polyatomic groups. And because they're polyatomics, they're ions. And ammonium is actually our positive polyatomic that kind of acts like a metal here, since metals are the ones that form those positive ions. So we have our ionic compound here. We name that group as it is, ammonium, and the group that it's attached to, CO3, we find that to be carbonate, right? Carbonate on the back side. In this case, we have copper. Well, copper is a transition metal. So copper can take multiple charges. So when we name copper, we know this is copper. We need to make sure that we put a Roman numeral in to identify what charge it chose. Copper, and I know this is ionic. Again, copper is a metal. And so what I do is I work backwards. All right, this group right here, NO2, we can name it right now. NO2 is a nitrite group, Nitrite, it's a polyatomic. And we look at the charge. We'll always know the negative ion's charge. And so we know that 1 nitrite is a -1. But we see that we have 2 of them, right? 2 of these nitrites. So overall, if I have 2 -1s, the negative feel is -2. Well, I need this overall charge to be 0, and this formula is already balanced. So I have the right amount of copper here to balance out a -2. I only have 1, so the charge that the copper takes has to be the +2 variation of it. And because of that, now I know what number goes in here. All right. An easy mistake to make is just putting the Roman numeral of how many atoms of that I have in the formula. Kind of like if you looked at iron 3, you might be like, oh, that's 3 iron. But no, right? It was 2 because the 3 is not how many. The 3 is just the charge that it takes. And that's why transition metals are a little bit wonky to work with. For J and O, no. It is not ionic. It is covalent. And then we can name this. And now because it's covalent, remember, I have to use prefixes in the name. All right. And so nitrogen is by itself, or not by itself, but there's only one. So we never use mono for the first. We use all the others, but not mono. Nitrogen and then oxygen, there's only one. This is the time that we do include mono, and we change it to oxide, right? We change the ending of the second name, never the first. This one is covalent as well. Carbon and chlorine are both nonmetals. Prefixes again, and let's say it again. Carbon, only one. I just name it as is. 4 would be tetra, and of course chlorine, we change the ending to chloride, show that it's bonded. And then last one, Al, that is ionic because it is aluminum, which is a metal. Aluminum is not a transition metal, so we don't have to worry about the Roman numeral to designate that charge. It always has a positive 3 charge. And then we see that the group that it's with is a PO4 group, which is our phosphate group. All right. Completing the table. This one's pretty straightforward. Valence electrons, alkali metals always have 1. Alkaline earth, 2. Halogen, 7. Noble gases, 8. The ionic charge, well, alkaline metals, they want to lose that 1, become more positive. Losing 2 for the alkaline earth metals, become positive 2. Halogens, again, they want 8. So instead of losing 7, they're going to gain 1. That's going to become negative. And, of course, the noble gases, they do not form ions. And that's because they have a full octet already. And then everybody wants to be just like the noble gases because they already are. Bohr model, kicking it back a couple of units. Bohr model, we can take the nucleus. So what I'm going to do is I'm just going to draw a nucleus with just designating that it is carbon. All right. Usually we would put protons and neutrons in there. I don't give you a specific isotope. I'm more concerned that we can identify how many electrons go on the outer valence or outer rings. So I know that carbon is in the second period, which means that it will have 2 rings around the nucleus where those electrons are going to go. The first ring is the first period. It can only hold 2 electrons, and the other 4, for a total of 6, go on that outer side, right? Protons equal 6, neutrons equal, we don't know, right? Doesn't matter right now for the sake of simplicity. We're just going to say the electrons must equal 6 for an atom of carbon. The Lewis dot is much nicer. All we have to do is take the valence electrons, which of course are the 4 that are on the furthest shell, and we have our dot, making sure that we don't pair up until we need to. All right. So going through this, the electron configuration, again, wherever it ends, we can identify what element it is, because we again are here talking about a neutral atom. So we see which element ends in 4p. So I go over here and I see the p's, of course, are all of these here, the last 6, right? Not helium. Helium's part of the S block. But we say, okay, 4p. Well, this would be 2p, right? This would be 3p. And of course, 4p would be in the 4th period. And we say that, oh, look at 3 in 4p3, that is arsenic. So we have actually identified that through the electron configuration, the element is arsenic, which is a S. How many electrons total? Well, all we have to do is add up those superscripts there, and we end up with 33. How many valence electrons? Well, valence electrons are based off of the ones that are in the furthest shell, which ends up being 4s, right? The 4th energy level here. And we just add up the 2 and the 3, we get 5 valence electrons there. And if we were to draw a Bohr model, how many energy levels? Well, as we've stated, the highest energy level we see is 4, so there would be 4 shells there, 4 energy levels around that. Down here, 4 isotopes that occur in nature, sulfur 32, 33, 34, 36. Which of the 4 is most abundant? Based on this average, remember these are all weighted averages because they all have different percent abundances. And so since it's a weighted average, this value, that average mass, is going to skew closest to the most abundant isotope. So all we have to do is look at this average, and we see which of these masses, which of these isotopes is that the closest to. And of course, we see that sulfur 32 is the closest. So we have sulfur 32 is the most abundant. Again, defining, this is just again a little bit of review. Compound is a chemical bonding of 2 or more different elements. Right? A chemical bonding of 2 or more different elements. Think of it as like a compound sentence where you have two parts of the sentence that create one thing, right? And so we go in, we say, okay, well then what's an element? Well, element is what we consider to be the simplest form of matter. And again, not to be confused with an atom, which is the smallest unit of matter that we can measure. The simplest form of matter that can exist is an element that's by itself, right? One of the elements out of the 118 that we have on our periodic table. So if I were to look at the periodic table again, I would say, oh, wait, anytime I have an element, right, I see it's an element because the symbol has a capital letter. So we can also simplify it and say, well, the elements are on our periodic table when we're reading it, the ones that have just the capital letter in front of them. And that's kind of a little more simplistic way of thinking about it. Heterogeneous mixtures are physical combinations, right? These are what mixtures are: physical combination of pure substances. And you're like, well, what are pure substances again? These are the compounds and elements. When they're by themselves, they are pure substances, right? So we're basically taking elements and compounds and we're putting them in the same space. That's why we say physical, because they don't actually change chemically. They don't turn into something else. They're just in the same space. But heterogeneous mixtures are non-uniform, physical combination of pure substances that are not uniform. All right, I'll do some quick example here. An easy one to say is like milk and cereal, right? You can identify the different parts of that. They're both in the same space, mixed together, but they are identifiable. Whereas a homogeneous mixture is a physical combination of pure substances. Of pure substances that are uniform, right? Just like teams use uniforms to, make sure that everybody knows what team they're on, right? So that they look the same in comparison to the other teams, right? That's kind of what the homogeneous mixtures are. So they are uniform. So that's something like any solutions that we can think of. So like Gatorade, lemonade, so on and so forth. So there are a couple of examples of that. And last but not least, using kind of these terms just to identify what these things are. This is actually a pure substance. And it's a pure substance because this combination is the only thing that's in this space. So I know it's a pure substance, and it's a pure substance of compounds, right? Because, well, I just say one compound, but because these things that are bonded together are different, right? And that's the definition of a compound. These last two, we can see they're definitely mixtures because not everything in this is the same. And so when we're looking at this, let's see what they're mixtures of. Well, this is an element, right? Because it's one type of thing. This is another type of element because it's different. And then this is a compound, right? Because it's two different elements bonded to one another. So this is a mixture of two elements and one compound, right? Again, elements and compounds are pure substances by themselves, so we're mixing those pure substances together. And we can do the same thing over here. And I'm also going to put compound and molecule, right? Because a molecule is any grouping of those elements there, and or those elements, whether they're the same or different. Here I have an element, and then I have here again a compound, or not a compound. I'm sorry, a element as well, because it's the same thing that's bonded to itself. So it's not different, but this is also a molecule because it is a grouping. All right, so I hope this helped. I would definitely focus a lot on the difference in rules, right? There's a lot, I understand, but if you do those practice activities that we had, then this should be pretty helpful. All right, if you have questions, again, please let me know.